Welcome to ECECS 552, Lecture on Performance and Cost. Performance and cost are complex issues, and many factors come into play when we're trying to assess them. Let's look at a quick example based on the airplane industry. If you look at the 4 airplanes that are enumerated in the following table, which of them would you say has the best performance? We could consider the number of passengers, and clearly the 747 accommodates the most passengers. If we look at range, the Douglas DC-8 actually has the greatest range. If we look at the top speed, the Concorde actually wins out. So the questions that arise are actually more complicated than simply looking at a single metric. When we're speaking about performance and cost, we really have to figure out what it is that we care about. Do we care about passenger capacity? Do we care about range? Do we care about speed? Do we care about perhaps fuel consumption in this day and age? These are all important issues that we have to agree upon before we can really make any meaningful comparisons in terms of performance and cost of airplanes, but also of computing systems. So when we talk about computer performance and computer cost, how do we decide which computer is fastest? Again, it's not so simple. Just like in the example with the airplanes, depending on what we're trying to do, let's say we're trying to do scientific simulation, where we're trying to simulate the behavior of real-world systems, complex systems. Typically in these kinds of applications, floating point performance, or the ability to do floating point computations rapidly, is most important. However, if I'm an app developer writing applications for my iPhone app, program development work typically requires very high levels of integer performance so that the code that I write can be compiled for my platform as quickly as possible. A third example might be database workloads. If I'm storing the warehouse database and the purchase orders and so on for a particular website, I'm storing those in a relational database, and typically these databases are very large, so they have a very large memory footprint. In fact, oftentimes the database is stored out on disk, so input-output performance becomes very important. So for these kinds of applications, we actually need very good memory performance, very good I/O performance, and the CPU performance is almost secondary in these cases. So depending again on which of these things we're interested in, and perhaps what mix of these things we're interested in executing on our computer system, these different factors and these different components of the overall performance become more or less important. So if you're interested in buying the fastest computer for the task that you want to run on it, you need to really understand that task or that workload. And you can understand that by measuring it, analyzing it, and projecting its performance on that system. Of course, oftentimes when we're dealing with performance analysis of computer systems, we're actually still in the process of designing those systems. We don't actually know what they're going to look like, what features they're going to incorporate, etc. So when the process of designing this, we have to also be able to make projections about this performance without actually being able to measure it, because the system that we want to measure does not yet exist. And in this process, it's also very important to pay attention to cost. It's sort of trivially true that if you don't care about cost, you can pretty much get any level of performance that you want. But the reality is that in all applications and all scenarios, we do care about cost, and so we always have to take that into consideration. That's going to be a big part of the sort of engineering trade-off analysis that we learn about in this course. So looking ahead to where this lecture is going, we are going to talk briefly about time and performance and how those relate to computer systems performance. We'll introduce the iron law of computer performance. We'll talk about some metrics that are commonly used, like MIPS and megaflops. We'll talk a little bit about which kinds of programs we want to measure and how to average them if we're trying to understand the performance of a collection of programs instead of just a single program. And finally, we'll introduce Amdahl's law, which is an important analytical tool that we can use to understand a computer system's performance and behavior. Before we can really usefully define performance, we have to think a little bit about what is important to whom. For example, we can think about performance from the perspective of the computer system user. The computer system user typically cares most about the elapsed time for whatever program they're trying to run. You can really think of this as the difference between the ending time and the starting time. That would be the response time. However, a computer center manager might care an awful lot more about the completion rate, so how many jobs per second are actually being successfully executed in this computer center that he or she is managing. This would be called throughput. So let's think a little bit about response time versus throughput. If we think about the throughput of a system, is that always inversely proportional to the average response time? Well, no, not always. That's only true if there is no overlap between the jobs that are executing or the programs that are running on the system. However, if there is any overlap, then the throughput is going to be greater than the reciprocal or 1 over the average response time. Think of this in the context of, say, a lunch buffet. So let's say the lunch buffet has 5 entrees to load onto your plate as you're stepping through it. If each person takes 2 minutes per entree, then throughput would be 1 person every 2 minutes, because as I move from one entree to the next, another person is going to move in and take my place at the previous entree. However, it's going to take me 10 minutes to fill up my plate, because I'm spending 2 minutes on each entree and there's 5 entrees. So my response time is actually going to be 10 minutes, but in fact my throughput in this particular case would only be 2 minutes. If that were not the case, what would the throughput be? Well, if the 5 people at the buffet are not simultaneously filling their tray, creating the overlap that we're talking about here, then without that overlap, the throughput would be 1 person every 10 minutes, because you would have to proceed through all 5 entrees before anyone else could begin with any of those entrees as well. So enough about lunch buffets. What is it that performance means for us as computer architects? It basically means the time spent running a program. We call this the CPU time. Intuitively, we would expect that a bigger number should indicate faster or better performance, so typically we will define performance as the inverse of the amount of time spent. So where x in this case, 1 over x time, where x would be the response time, the CPU execution time, etc. Typically, in systems that are interacting with input devices and output devices, there's an additional component to the elapsed time that you observe. So there's some time spent executing on the CPU, but we have to add to that the amount of time spent waiting on that input or waiting on that output. And typically these I/O devices are much slower than CPUs, so if your application is doing a lot of input or output, this is oftentimes going to be the dominant term in the elapsed time. However, for the purposes of this lecture, we'll be focusing on CPU time. We'll have much more to say about input and output later on in this course. At a very high level, what can we do to improve performance? Well, again, if we think about performance in terms of either response time or throughput, we can improve one or the other by, first of all, let's say adding a faster CPU. If my CPU is faster, the response time for each individual job will be lower, so that'll be improved. But throughput will also be higher, because we'll be able to get more work, more individual jobs through the system. So we'll give that option a check plus. This is something that we have been trying to do as computer architects for many decades now, build faster individual CPUs. However, we can also add more CPUs to the system, and this is something that started happening about 10 years ago in the PC space. We started getting what are called multi-core processors, and these have, of course, have become very widespread in just about all systems and all platforms now. And what we do here is we don't really do much to help response time, because any individual job is still only going to be able to typically run on a single CPU, and so it won't complete any faster, so its response time won't be any better. But because we'll have multiple cores or processors now that can execute jobs in parallel, we will be able to increase the throughput roughly proportionally to the number of cores that or CPUs that we're adding to the system. If we want to do performance comparisons of systems, for example, like we have a machine A and a machine B, we can basically say that a machine A is n times faster, or sometimes we abbreviate the times as an x, nx faster than the machine B, if and only if the performance of A divided by the performance of B can also be expressed as the time of execution on B divided by the time of execution on A, because performance and time are inversely related. That would be then equal to this ratio n. We can also say that a machine is X% faster than another machine, if and only if the performance of A over the performance of B, or again, the time of B over the time of A, is equal to 1 plus X over 100. So here we're just expressing the speed up as a percentage. So for example, if the time to execute a program on machine A is 10 seconds and the time to execute it on machine B is 15 seconds, then simply by computing the ratio of 15 and 10, we see that A is 1.5 times faster than B, or we can also express this as a percentage by saying A is 50% faster than B. If we want to develop a slightly deeper understanding of what's going on here, we can start thinking now about a program as being broken up into a sequence of instructions that the hardware executes. The hardware really is not aware so much of programs, it really just fetches and executes one instruction at a time. And that's really the unit that it's interested in. At a much lower level, the hardware will break these instructions themselves further into smaller steps that each will take typically one machine cycle to execute, and that there's a lower level state machine then that controls the hardware in the processor that will change state every cycle. So just as a quick example, we can think of a typical processor that might be in your smartphone, like a Snapdragon from Qualcomm, running at 1 gigahertz. It's going to run 1,000 million cycles per second, where each cycle now will consume 1 nanosecond of time. Conversely, a 2.5 gigahertz Core i7 processor from Intel that might be in your laptop or your desktop will run at 2.5 billion cycles per second, and each cycle will now consume 0.25 nanoseconds, or 1/4 of a nanosecond. Let's dig a little bit deeper. So we talk about instructions, and we talk about cycles, and we talk about programs. We can put all of these concepts together into what's known as the iron law of processor performance. Like we've already discussed, we like to think of the performance of a processor in terms of the time it takes to execute a given program. So time over program. We can further subdivide this concept of time per program into 3 constituent components. The first of these components is really the instructions that you have to execute to complete that particular program. So this would be really the code size. This really depends heavily on things like the instruction set architecture itself, how complex or how simple are the instructions, how much work can you get done with a single instruction. And a lot of this really comes to play when you're actually designing a new instruction set architecture, which is something that happens, very, very rarely in real practice. The other thing that really affects this term heavily is the quality of the code that your compiler generates. So there's a lot of effort that goes into building compilers that can optimize the number of instructions that are needed to execute a particular algorithm. And if your compiler is designed very well, you can bring this number down significantly for a particular algorithm that you're interested in executing. The second term is the cycles per instruction term. This really is a function of the implementation. So the processor designer now has an opportunity to make a series of complex trade-offs regarding how the hardware itself is built to execute the instructions that will determine whether a particular instruction will execute in a single cycle, 2 cycles, 5 cycles, 50 cycles, really anywhere in that range depending on the requirements of that instruction and how the hardware, the pipeline, the control logic, the data path, all the pieces of the processor itself are constructed. So that's the second term. And the final term really is the time per cycle. So at what clock rate are you able to run now the hardware that you've designed to execute these instructions? And this is really up to the chip designer. The realization is up to the chip designer, and this is something that will vary from one implementation to the next. So it could be that maybe 5 years ago you could buy a particular ARM processor that would go into a cell phone that ran at 400 megahertz. Today, you can buy an ARM processor that's in many ways very similar to the one that you bought 5 years ago, but because the chip has been redesigned very carefully now for higher performance, that same part will run maybe at 1.5 gigahertz or even higher than that. Now, all 3 of these terms, of course, interact with each other in complex ways. So if we have a particular instruction set architecture that has complex instructions in it, it might be very difficult for me as a processor designer to come up with an implementation that keeps the number of cycles per instruction low, because inherently those instructions are doing more work, so it's probably going to require multiple cycles of activity to execute those semantics. Similarly, if I choose an implementation where I try to minimize the number of cycles per instruction, that might become very, very difficult for me to build that, to realize that as a chip designer at a very competitive frequency. So we actually see in the industry designs where these terms are very, very different. Even for the same instruction set, running the same program, we'll see designs that are optimized for cycles per instruction that might have a lower cycle time, or we might see designs that sacrifice the cycles per instruction term that grows, but are running at very, very high frequencies. Again, just to reiterate the three terms in the iron law, the instructions per program is the instructions executed, not the static code size, and it's determined by the algorithm itself, the quality of the compiler that generates code from your high-level algorithmic description to the actual machine-level instructions, as well as the instruction set details themselves. The second term, cycles per instruction, is again largely affected by the ISA and the organization of the CPU, and it really is about describing the overlap that exists among instructions. So the more overlap you can create among instructions, the better effective cycles per instruction you can achieve. Just like in that food buffet line, if you can get 5 people to the buffet ladling food onto their plates in parallel, you'll spend less time per person now actually pushing them through, and you'll improve your throughput. And the final term, time per cycle, again, is determined by all of the above, as well as the particular technology that the processor is being implemented in, and again, the organization, and also all kinds of clever circuit design techniques that we've developed over the years. Now, our goal, of course, is to minimize the time, which is the product of these three terms, not the isolated terms themselves. This is very important to remember because it's a common error to actually miss terms while devising optimization. So, for example, you might make an ISA change to decrease the instruction count, but that ISA change will actually lead to a CPU organization, which is very difficult to design with a high clock frequency, so ultimately you end up with a slower clock frequency. So the bottom line here is these terms are interrelated, and you have to be very knowledgeable in all three in order to make the right trade-offs and right decisions in each one. Some other metrics that you might have heard of floating around out there are MIPS and megaflops. We'll talk briefly about these. MIPS is really just millions of instructions per second. You can compute that as the instruction count divided by the execution time times 10 to the sixth. Or conversely, you can express it as or compute it as the clock rate divided by the CPI, again, times 10 to the sixth. MIPS, of course, now has some serious shortcomings, so there are some limitations to using it that we'll talk about on the next slide. Just as an example of some of the problems with MIPS, you might think that you might correctly assume that a machine that doesn't have any hardware support for floating point operations versus a machine that has to emulate floating point operations in software, you would expect that the machine with floating point hardware would give you much better performance. This used to be a feature that you had to pay extra for back in the 1980s. If you bought a CPU, it didn't have any floating point hardware. You had to buy an extra coprocessor, and then later on, you could buy a more expensive version of the processor from Intel that included hardware support for floating point. So in this particular scenario, you might have a floating point operation like adding two floating point numbers together. It might take 50 single cycle instructions without any direct hardware support for it, whereas with floating point hardware, it would only be a single 2-cycle instruction to perform that floating point addition. So you would expect that intuitively, you would expect that adding this hardware would give you better performance, and that's in fact true. There's a number of things that happen here. So first of all, when you add the floating point hardware, the CPI increases. And why is that? Well, you basically go from 50 cycles to execute 50 instructions to now 2 cycles to execute 1 instruction. So that's actually a higher CPI. The instructions per program decreases, and the reason here is, again, instead of 50 integer instructions to emulate that single floating point operation, you just have that one floating point operation. And of course, as you expect, the total execution time decreases as well. You go from 50 to 2 cycles. But the MIPS in this case gets much worse. So 50 MIPS in the baseline case now becomes 2 MIPS. And so if you're using MIPS as your metric of performance, you would think that adding floating point hardware actually made your performance worse. Obviously, that's not the case. And that's something that we have to keep in mind. The real problem with MIPS is that it ignores the program. It's usually used to do things like, quote, peak performance. Peak performance is really just something that's you can trust that you will never exceed that level of performance on that particular system. It's measured or estimated under ideal conditions. When is the use of MIPS okay as a metric for performance? Well, if you're running really the same binary generated by the same compiler, running the same program, but you're just running on two different implementations. So you might be running on one of the new Jaguar cores from AMD that's in the PlayStation 4, or you might be running it on Intel Core i7, which is in your desktop PC. In that case, comparing MIPS against MIPS, there's really no problem, because the instructions per program term, which is the one that was changing in the previous slide most dramatically, that is now constant. It's not changing, and so we can factor it out of our performance comparisons, which is exactly what MIPS, when we use MIPS as a comparison, that's what it's doing. So that's a safe thing to do and a valid comparison to make, but only in that circumstance. Another metric that you'll sometimes hear used is megaflops or mflops. It's the number of floating point operations in the program divided by the execution time. This again assumes that the number of floating point operations that you need to implement a particular algorithm is independent of the compiler and the ISA. This is often a safe assumption to make for numeric codes, where typically the matrix size, let's say you're doing matrix multiplication, is really what determines the number of floating point operations per program. There's really no way to change that via compiler optimizations. You still need to, multiply every element in every row against every element in every column to compute the resulting dot product. However, this is not always a safe assumption to make. Even in floating point applications, again, there might be differences in the ISA. You might not have support for a floating point divide instruction, for example. In that case, you'd end up with incomparable megaflops ratings for the same program running on two different platforms. The other issue that comes up sometimes is these terms called relative MIPS and normalized megaflops. These are really mostly just marketing terms, and you shouldn't pay any attention to them in the context of any kind of scientifically valid discussion of performance. Just recapping here, the safest thing to do is to use only time when you're comparing performance, and be very careful when reading, especially if the details are omitted. And again, be wary of peak performance. Again, that's guaranteed not to exceed. Doesn't necessarily tell you anything meaningful. Okay, let's go back to the iron law and look at a brief example. So assume you have a machine A that has a clock period of 1 nanosecond, runs at a CPI of 2 cycles per instruction for a particular program X. We also have a machine B that runs at half the frequency, so twice the clock period of 2 nanoseconds, but its cycles per instruction is much better, only 1.2, again, for the same program X. Which of these machines is faster, and by how much? Well, again, according to the iron law, what we really care about is the time per program, which is the product, again, of these three terms: instructions per program, cycles per instruction, and seconds per cycle. So again, we plug in the values given here for machine A, and we can come up with a factor of 2n for machine A and a factor of 2.4n for machine B. What that tells us is that the performance of machine A is going to be better than the performance of machine B. Again, if we take the ratio of the two times required to execute the program, we end up with speed up of 1.2 for machine A. So machine A can also be said to be 20% faster than machine B for this particular program. Let's extend this example a bit further. If we keep the clock of A at 1 nanosecond and the clock of B at 2 nanoseconds, what would we have to achieve in terms of CPI on machine A to get equivalent performance for the two machines? Well, again, we compute the ratio of the time on B and the time on A. We set it as 1 for equivalent performance, and then we plug in the iron law equation for both of these cases: n times 2 times 1.2 for machine B, n times 1 times the CPI of A for machine A, which is again what we're solving for here. Some of these factors cancel out, and we rearrange a few terms and simplify, and we end up with a CPI of 2.4 for A to get equivalent performance. Flipping things around a bit further, we could also look at this from the perspective of fixing the CPI of each machine. In this case, the CPI of A is fixed to 2.0, and the CPI of B is fixed to 1.2. And to achieve equivalent performance, and if B has a clock rate of 2 nanoseconds, what would have to be the clock period of machine A to match the performance of machine B? Again, we simply compute the ratios of the times, we plug in the values again, we cancel out the terms that are in common, we rearrange terms, and we solve for a clock period of A of 1.2 nanoseconds. We also
Summarizing
talked
the
briefly
lecture,
about other metrics.
we can talk
MIPS
about time and performance,
which are
when
not
we're comparing
particularly
two
useful,
machines,
but
in this
can be
case
applied
machine
in
A and machine
specific
B,
circumstances.
as having a
And
factor
just a
of n
final
difference
warning,
if the time to
beware
execute
of
on machine
concepts like
B
peak
divided
and
by the
beware
time
of
to execute
omitted
on machine
details,
A
because often the
is
truth is hidden
that
behind
factor
them.
n. We can break this down further, performance down further, using the iron law, which again measures the time to execute a particular program into three component terms: instructions per program or code size, cycles per instruction, as well as cycle time.